I wish I could be there in person, but unfortunately I can't because I'm getting married here in 3 days, so there's just a lot going on at home. As said, I'll be presenting my work on a fast Prakriyā generator, and I'd like to first get on the same page on what is a Prakriyā. And I'll be very brief here. It's a derivation, according to Paninian rules from Sanskrit grammar, of a specific word or expression form. So here you can have an abbreviated Prakriyā of the word bhavati, meaning is or becomes. So what is a fast Prakriyā generator? The easiest way for me to convey that is to show you a quick demo. So I'll just click this link here. This is my GitHub repo with different tools that I built. I just called this repo Vidyut for short. Go to Vidyut Prakriyā, and there's a link to the demo here, which I'll open up. Let me stop and just make sure that everything is presenting correctly. Can you see my screen?
Yes.
Okay,
yes.
I'll continue. Okay, so everything you're about to see now is running locally in my browser. Now that the demo is loaded, there's no connection to a server or anything like that. So I can click over here and click some dhatu like bhu, and I can
Arun,
see all of its forms.
can you zoom in?
Yes. Is that better?
Yeah. Yep.
Great. So all these forms are generated in the client side, and I can create different versions of this, like using a sananta prakriyā like sun, or nich, or young, or youngluk as well. I can change this to karmani prayoga and add an upasarga as well. And again, this is all happening in the browser. And if I click one of these words, I get a step-by-step computational derivation of this word form, showing the rules that apply with links to ashtadhyayi.com, showing how the word was created ultimately. And at the end, we have our final result, parabo bhuyate. So I'll return to this later in the presentation. So I want to briefly convey what the project is. So continuing from here, why care about this? Why is this an important problem? There are three angles that I think are interesting. The first are study tools like ashtadhyayi.com, sanskritabhyas.in, Sanskrit Heritage Site, Sanskrit Library, Samsadhani, and so on. Having an accurate list of Sanskrit words to consult is useful for students and anyone curious about Sanskrit grammar. Second example is dictionaries, using sanskritdictionary.com as an example here, or kosha.sanskrit.today. It's nice if a dictionary allows searching by a specific word form, like gachati, instead of just the base form gam. And then as a third example, alluding to a talk from a couple of days ago, or I guess just yesterday, spell checking. So if we have a rich list of Sanskrit words, potentially we can offer a better spell checking experience too, for anyone who needs to have high quality, well-formed Sanskrit text. So what have people tried in this direction so far? There are many different approaches to cover. In the interest of time, I'll just touch on two. The first is this XML formalization work from sanskritlibrary.org. I don't know about the details since can't speak to them intelligently, but from what I understand, it's a very deep and precise formulation of different Paninian rules and their semantics in an accurate Paninian way. And here you can see an example derivation of the word bhavati, I believe, is the page that I pulled this from. And then another example, which is more akin to the spirit of my project, is Sanskrit Verb, which is a successful project from Prakriyā Pradarshini, published in 2015 by Drs. Dava Patel and Shivakumari Khatri. So here you see Prakriyā displayed on ashtadhyayi.com, showing again the derivation of the word bhavati. And the technique of this approach is relatively simpler. It uses regular expressions and string matching. But the big advantage of it is that it's very simple to understand, and it's actually deployed in real sites that people are using. I think it's a tremendously exciting and inspiring project, and I took it as inspiration for the work that I'm presenting here. So why build something new, given that these systems exist already? There are really two reasons that come to mind for me. The first one is speed. As a simple question to frame this, how long does it take to test 180,000 words? This would be 2,000 dhatus and 90 different forms for the 10 lakaras, and then the 9 combinations of purusha and vachana. So if we could test it 10 of these forms per second, it takes about 5 hours. So testing a single change would let could test about 2 in a single working day. But with each order of magnitude improvement that you get, it becomes easier and easier to test. And ideally, we're aiming to this threshold here of 100,000 words per second, which means that if you can do something like that, you can test a code change incredibly rapidly, which makes it easy to iterate and build out the program and make sure it's well-formed. And the second is reuse. So if we're implementing a program like this in a language like PHP, it's limited generally to a PHP web server or something you can call through a REST API, let's say, for example. But the downside of that is that you can't easily reuse that system. So one advantage of what I presented here, and I'll explain how it works, is that it both works totally on client side in a browser, but can also work in a backend server and on an app as well, using the same code without having to rewrite anything. So that's a tremendous advantage for deploying something complex like this. So how did we build it? I'm going to touch on this from a couple different directions. There are details in my paper, and I'm happy to dive in the Q&A. In the interest of time, I'll keep some details very brief. First is a very narrow scope. So there's no explicit model of anuvritti, or the context inheritance that the Ashtadhyayi uses to condense rules in a small format. There are specific rules of anuvritti. I haven't explicitly modeled those in any way. Likewise, there's no explicit model of conflict resolution, the method by which we choose which of two rules can apply if they have equal co-application. I'll talk about how I avoid this, and it's a pretty simple approach of just choosing a fixed order. But this is, I want to be very clear, an important theoretical issue that I have no perspective on in this paper. Likewise, I'm not taking any variant interpretations of a rule. So if the tradition disagrees on how a rule should be taken, I tend to go with what the Kashika Vritti says in general, or Siddhanta Kaumudi as well. And then there's minimal use of traditional grammatical theory. This is due to my own limitations mainly. For example, I was halfway through development of this before I had even heard about the Paribhasha and the Shekara. So there are just some limitations in my own background knowledge. But the reason that I can confess that so freely is the program seems to have worked out very well despite that, which is perhaps interesting on its own and a subject for future discussion. So another kind of a method of approach is the choice of programming language. And I, after exploring a few options, decided to go with Rust, which is a very fast and reusable language. And here you can see an example from our API and documentation in case someone wants to get started. So if you aren't familiar with Rust, you can think of it as a language that roughly has the speed of C or C++, with the tooling of something like, let's say, the Node ecosystem, and some properties of OCaml as well. It has a mix of kind of all these languages at once, and what it's trying to promise is the speed of a low-level language like C or C++, with safety on top, which means that it's easy to build a complex program and have speed without having segmentation faults. That's too much of a technical detour mainly, but I found it a tremendous joy to work with this program and build it with Rust, which is why I'm advocating for it here. Here's just a quick view of our data model as well. I model a Prakriyā as a list of terms, and a term is just a string with some metadata on top. Tag is an enum, so one of a list of values, and this is basically a sanya with other flags on top. And there's some basic logging as well. I can go into the details later, but I just want to convey there's a structured model, and this is what it looks like underneath. And likewise, there's a structured argument model, a way of passing parameters into the program to derive specific words. So here you can see I can request deriving a thing anta with the dhatu, prayoga, lakara, purusha, and all of that. The dhatu can be either a mula dhatu or a nama dhatu. And then the mula dhatu can have an upadeshika form, which I just called upadesha out of a little bit of laziness, one of the 10 ganas, and optional antargana, and other details there as well. And technically, the prefixes shouldn't be part of the mula dhatu. This was just easier during earlier development. I'll probably remove that somewhere else later on. I also adopted a simple control flow, again, taking inspiration from Sanskrit verbs. So I said earlier that I have no explicit model of conflict resolution in rules. What I do instead is just a very simple ordering. So here's an example of 3 rules on the right, on the left. Jholantaha, adabhyastat, atmanepadeshonataha. So here I order them explicitly with a simple if, else checks. And you can see the specific rule that's being run. I have a comment here with an example that is produced by the rule just to keep the design straight while I'm iterating. And here's some basic examples of the API. So I'm looking at the last term in a list of the Prakriyā, looking at the base term and it's an abhyasta, applying these, and so on. I also have support for optional derivations. The mechanism here is quite complex in details, but easy to convey the gist of. During a derivation, I record whether a rule is optional, meaning if it's marked with va, vibhasha, or anyata rasyam. And then after the first derivation is complete, we try permutations of those rules that we saw and kind of draw out all possible paths for each word that we could generate. And again, I can go into that in more detail in the Q&A. Just in the interest of time, I'll keep that brief. So what can the system generate, given all this work so far? First, obviously, is a list of words, a list of well-formed words. So here is just a snippet of Kattari Tingantas without any special upasarga or anything like that. These words are relatively straightforward, but I also have nijantas, sanantas, and other verb forms like this. This is quite straightforward, so I'll move on. And likewise, we have this Prakriyā as a structured data object that represents the grammatical rules that are applied for any given word. So here we have part of the derivation of abhut, which is the lung lakara of bhu dhatu, bhu saptayam. And here we can see the exact rules that are being applied along with links to ashtadhyayi.com in the UI. But in a program, we could see the specific rule code that was applied and maybe show some interesting data about that rule if we so choose. Going into details, we have strong support for optional forms as well. So here's an example of our test for rule 3136. And then going into the details, this program has very strong support for Tingantas. So you can here see the test for 3170. Subhantas as well have reasonably strong support. So here are some examples from Siddhanta Kaumudi 291. Kridantas as well, with examples from 31126. Unadi Pratyas as well are supported, supporting about 500 rules from the Unadipata right now, with more coming soon. And I'll pause here also very quickly to note that the dhatus are encoded in SLP1 transliteration. I have no strong opinion between SLP1 or WX. I just chose one that I was familiar with, and I wanted something very condensed where one byte represented one phoneme, which is just easier to work with. And then likewise, there's strong support for tatitantas as well. Here in this test function, you can see that I'm deriving these specific words on the right in the sense of tatra jata. And if this kain pratyaya is not available in this sense, the derivation won't work. So I'm testing both that the pratyaya can be added to create that form, and that also that is available only in the specified sense. Likewise, there's basic support for samasis. This is still quite early, so you can see some tests from 2.1.1. And stri pratyayas as well, and you can see some examples from Ajaditashta. So we have Aja, Devadatta, and so on. Devadatta, and so on. There's also limited support for nested expressions. I've tested this in some contexts, but not others. So here we have the result of putriyati. We start with the pratipadika putra, and we mark this as the namadhatu created with the kyach pratyaya. And this test is implemented and passes. Likewise, we can create a kridanta and add a subpratyaya to the end. I've tested this with some basic expressions as well. So if we have two subantas and a single expression, that can be generated as well. But I haven't battle tested this thoroughly, so it's a little experimental. And likewise, support for svaras is also experimental. I have support for very limited things like chit, lit, tit, nit, and so on, mainly from this section of the text, pada 6.1. And here we have some examples of narayana, charayana, and the anudatas are hidden here, so I just don't have to type them out, but they are modeled explicitly by the program as well with the udatta at the end. So how do we know this program works, given what I've said earlier about my kind of a background and focus on engineering and relative lack of familiarity with the tradition? Well, mainly I've leaned on the tradition. So if we take this rule from the Kashika Vritti, for example, these words in green are positive examples of the rule and how it applies. And these words in red are negative words or counterexamples to show where the rule doesn't apply. So to my mind as a programmer, these stand out as unit tests that are very convenient. So we can just turn them into a unit test like so. So here in this previous slide, we have a dukshat and a likshat and a paitsit and so on. And here these become examples that we explicitly generate and make sure we can produce. And notice also we have abadat and achidat because these are forms that are licensed as well. What this function assert is testing is that we can produce exactly the forms that are being specified given the input parameters. Likewise, we can test against the Siddhanta comedies. So again, if we take the examples from Jhantaha, we can turn those into a test. And I'm happy to walk through this as well at the end if there's time that allows it. And there's also something I use called snapshot testing. This might be a little unfamiliar. Essentially, in this test that you see here, I'm generating about, I think, 1.5 million forms and making sure that if I make some change to the program, the forms underneath are not changing. So I'm not testing if the forms are correct. I'm just testing if they're consistent with what I've tested previously. And to briefly convey some sense of the speed of this, if I run it right here, time make test all, this is running live on my computer right now. First, there'll be a compile. That's actually taking a bit of time. I'm not sure whether it's compiling right now. Anyway, I'll come back to this, I suppose. We can check back on that later and continue here. So how well does this actually work in practice, given these unit tests that we have and this testing regimen that we've tried? So I have a quality and a speed comparison to Sanskrit Verb, which again is an outstanding system I have really high regard for. I performed an exhaustive comparison that I mentioned in my paper, and there are a lot of very small wins that collectively add up to, I think, a higher quality implementation. Mainly it's due to the support of stronger optional forms in various cases, like Tanadi Lung forms or Garbani Lung forms as well. And in terms of speed, this is, again, kind of an inexact science, and it's an unfair comparison because I'm using a faster language and a second implementation that can go off the work of a predecessor. But in average usage, we see something like a 2 to 3 orders of magnitude improvement. And this is important for testing because it means we can run our massive test suite and ensure that things are well formed. Speaking of, I'm going to quickly check and see how this did. Okay, this ran in about 20 seconds with the compile, but if it's compiled already, you can see these running live. So each item going by, this is running about 200,000 different tests in the background, making sure we can generate certain verb forms. Now, if I open up one of these, like the young Karmani here, you can see the forms that are being tested underneath, and I'll try to zoom in so it's clear. So here it's testing the specific form, the dhatu, the gana, other metadata, the sanadi, the prayoga, and other information. So returning here, what next with this work? What can we do with it now that we have it? First are the applications that I talked about at the beginning of this talk in terms of having a higher quality list of Sanskrit words, showing derivations, maybe applications for dictionary tools. But more concretely, in the short term, I want to implement more rules. Current coverage is about 2,100 implemented rules. I can't get to full coverage because some of these rules can't be formally modeled, like Tadashishyam Samnya Pramanatvat. I don't know how to put that into a formal structure, so I'll set that aside. But in terms of practical rules that generate words, I'd say we still have quite a ways to go. More tests as well. I focus mainly on the correctness of word forms and have not focused on the correctness of Prakriyā. So I'm hoping to pull some examples from the book like this, the Paraniya Vyakarana Udaharana Kosha. And if I can pull those in, I think I can also justify the well-formedness of some of these derivations as well, because there are some artifacts that indicate that it is generated by a computer. And more sophistication as well. Let's see if I have time to pause here. Essentially, Rust has a feature called macros, which let you generate and rewrite code on the fly. And I'm hoping that we can apply this to maybe move away from if-else change and move to a meta-language representation and experiment with things like applying algorithms to order rules explicitly, for example. I think there's a lot of power that can be applied here to have the same runtime performance that I have, while at the same time letting us model things like different approaches to ordering rules in the grammar, just for interest. And then there are new tools we can build as well. I was just reminiscing the other day about the work that the Cologne project has done on digitizing Sanskrit dictionaries, so much so that I don't need to use a paper dictionary anymore. In the same way, I think that tools like this can allow us to move into digital grammar resources that are much more sophisticated than what we have now, that remove the need for a paper grammar book. I hope that I can type in a Sanskrit word and get a breakdown of exactly how it's derived, explained at a level that's appropriate for the student asking. So why does any of this work matter, to kind of conclude? First, we're producing Sanskrit words with rich structured data. So for example, if we derive the word gatva, we already know that it's created with va pratyaya on the gam dhatu. But we can also see that it's produced by a specific rule here. And we can ask questions like, what other words are produced by this rule? What other forms of gum might use this rule as well? And get more insight into the behavior of the class of words produced by this dhatu. Likewise, I think I validated that Rust is very useful for building fast and reusable Sanskrit tools. As a second experiment that I'm quickly showing here, this is a transliterator that I wrote in Rust recently that's running again in the client side that I'm hoping can become a standard transliterator backend that can be used everywhere as needed. And then likewise, I think this is an incremental step toward emulating the complete Ashtadhyayi. I want to be very clear, I've avoided certain key issues around rule ordering, anuvritti, and issues like that. But the advantage, I think, is we've made incremental progress toward a real system that is useful today for applications that I think are interesting. I want to just quickly mention some special thanks. These are in the paper, and in the interest of time, I won't call out specific names, but this is work that had a lot of small contributions for many people, and I'm very grateful for people who've contributed here. And likewise, I work on this project as part of a larger group called Ambuda. What we're trying to do is create interesting Sanskrit digital libraries and artifacts online. And you can email me here or check out some of our work here. I'll pause there. I went through that quite quickly, but I'm happy to take questions.
Thank you, Mr. Arun. Wonderful presentation. Yeah, this floor is open for questions.
What I see is so mesmerizing that the only thing I can say, I bow to what you've done, and I hope you continue. It's like a factory.
Thank you very
I'm
much.
looking like at a factory that is only starting to producing the verb forms. Let there be a lot of Sanskrit verb forms.
Okay. Any questions or observations, comments?
Thank you, Arun. It was a very nice presentation. And yes, this particular technology which you are using, Rust and other things, that is really very mesmerizing, I should say. The results are very mesmerizing. But at the same time, I was just thinking aloud, why do we need the derivation of all the verbs generated and stored? And why the need for that speed? And say, because as a Sanskrit student, what I feel is, yes, if I have a doubt, then at that point in time, I should get that information. So for that particular word, you can generate the derivation on the fly and show it. Why do we need to generate all these and store?
Very good question. So there's soft rule of program design, which is first you implement a basic system, then you make it correct, and then you make it fast. So my goal is not necessarily to make a fast program, it's to make a correct program. And what I found in early attempts at building something like this in Python, for example, is it would be very easy to introduce a bug and only find out about it much later because it wasn't uncovered in my test suite. So the reason I care about speed is the speed lets us run a very large test suite to make sure that there's no accidental change somewhere in the program. And during development, I've seen it be the case where I made what I thought was a simple, innocuous change and accidentally broke the derivation of several other words that I wasn't expecting to break. So that's the reason for the speed, number one. And then number two, for this web demo that I showed, for example, there is a slowdown that happens there when converting from Rust to WebAssembly. It's running in what's called WebAssembly. And the slowdown is not great, but I wanted to hedge against that by making the core program as quick as I could. And what that means is something like, if we load a page showing all the verb forms of a dhatu, that can happen basically immediately. If this program were, let's say, a couple of orders of magnitude slower, there would be a noticeable lag. And I also just personally, this is maybe not a wide application, I just personally like building things that are fast. And it helps me continue the kind of development flow and keep adding new features. So those are the reasons that I think it's worthwhile.
Good. So it's essentially a very quick feedback cycle.
Yes, exactly.
Yeah, good. Thank you very much.
Okay, let's thank once again to Mr. Arun Kumar for his wonderful work. Thank you, Arun.
Thank you. It's very late here, so I'll go to bed. All the best to everyone for the conference.
Good night. Thank you. 1 minute.
Yes.
So, Arun, all the best for your marriage.
Thank you very much.